Good morning, ladies and gentlemen. Welcome to our odor management workshop for anaerobic digestion facilities. My name is Craig Coker. I'm with BioCycle magazine and the moderator for today's session. A few housekeeping matters, if I might. The restrooms are down the hallway. Please put your cell phones on vibrate or on silent to respect our speakers. We have 5 private sector companies presenting at our lunchtime lightning round, up from the 3 shown on the agenda. So it's going to be a little bit more compressed. Those who are here that are presenting during that lightning round, please raise your hands. Okay, please introduce yourselves.
My name is Tim Bortolaff. I'm a business development manager with Biogas Solutions.
And sir?
Brandon Dixon from BioRep.
Okay, great. You'll hear more about these gentlemen and their companies during the lightning round. We have several very good presentations for you today, and we are also live streaming this for the internet. So there are a lot of people watching online. Keep in mind that all of these microphones are hot, so we don't want any hot mic mistakes. And this is sort of an experiment to see how this live streaming thing works out, and I think it'll be most successful. As we get started, before we get into the meat and potatoes of our workshop, I'd like to ask Bernard Sheff, the president of the American Biogas Council, to come up and say a few words. Bernie?
There sure aren't 40 people here. I mean, you only got 2 degrees in engineering and 4 years of college math, but there certainly aren't 40. This is exciting. To all you folks out there listening, I wish you could be there with us here, but this conference or this workshop started to take form about a year ago. The number one issue in the digestion area world right now is odor. We have a number of facilities that have been, unfortunately, are on hold right now or shut down, waiting odor control systems to be put in, or actually don't know if we'll ever get them back on. We take on projects across the country, as far as my company, in digester facilities that are having odor issues, and there are a number of issues that are causing this. But what we wanted to do today was sit down, get some of the top industry experts in what actually odor is. Odor is much different than, it's not just, well, you've got a, if you have a chemical, you can go after it. If you have an odor, many times you don't know what it is. And if you live next to a bakery, you might think that the smell of baking croissants in the morning is an odor, where the rest of us, or at least those of you that can eat wheat, think that that's a pretty cool morning. So we put this together. I'm real excited to have this opportunity. I also would like to just take a moment and say, if you're not a member of the American Biogas Council, first question is, why not? In fact, I should just have all of you come and tell me, give me 10 reasons why you're not, as opposed to me giving you 25 why you should be. The ABC is growing and expanding. We are the voice of the renewable energy from biogas in this country, and we have members both from we have members from Europe and from Canada. And are there any Canadians in the room? Thank you for coming down and surviving the gauntlet of the border, I guess it's become. So thank you for that. And I cook maple syrup every year. We have a farm, so I feel kindred to you. We'll all talk about maple syrup later. And its medicinal remedies. Again, going back to the ABC, and it is without a doubt, it's your voice. You need to join. You need to be part of this. We have 2 bills, one in the House, one in the Senate, and even with the tumultuous times that we're all living through, we've gotten support, and they're coming out. Patrick, they're going to be put out this week, right? I mean they're already out, but the stewardship bills.
We're expecting the Senate version to be introduced momentarily.
Momentarily on our bill. So if you're a member of the ABC, you can go around singing that song, I Got a Bill, up on Capitol Hill, because we got a bill, an Environmental Stewardship Act. Again, we're moving. We've got the same bill in the House, and we have support, and that's the biggest thing. We've got Republican support on all of these bills. So I hope you have a good work, find this very useful. I think the folks have put together great presentations. The lightning round, I think, will be very interesting with the vendors. These are the folks that are actually supplying and putting all these pieces of equipment into place. So I guess that's it. I made the introduction, and go ABC. And remember, we're the ones.
Thank you, Bernie. For the lightning round, we're going to have lunch served out here in the hallway, so you go out and get your lunch, bring it back in. We'll give you a few minutes to eat in peace and quiet and network with your colleagues, and then we'll ask each of our technology providers to do a 5-minute presentation, 5 to 6 minute presentation on their companies. Because we are live streaming this, we want to try to keep to the schedule as tightly as possible out of consideration for those who are watching online. So if you have questions, we run short. If you have questions of either a presenter or of one of the technology providers, we'll have time at the end of the day for some one-on-one networking and interaction prior to the reception tonight at 5 o'clock. Okay. The biographies of all our presenters are in your agenda package. I won't waste time with that because they're all very talented. Let's spend the time on talking about the real issues about odor management. And I'm going to start with your basic odor science 101. And this is a little bit on the technical side. It is on the midterm exam, so take notes. The reason we have to focus on odors in the field of organics recycling, whether you're digesting, composting, or both, is it is the #1 issue that affects the ongoing viability of facilities in our industry. There are more of our facilities shut down due to odor complaints than any other reason. And it really doesn't matter what kind of technology you're using. It's a very significant problem. And the reason it's so significant is that each of us perceives odors a little differently. I always open my odor management presentations with this question. How many of you like the smell of hepta-2-one? That's a chemical. Raise your hands if you like that smell. No, Michael, I should have known. All right, let me rephrase this question. How many of you like the smell of blue cheese dressing? Okay, how many do not? That's the difference between us as human beings. That chemical, hepta-2-one, is the chemical that causes blue cheese to smell the way it does. Half this room likes that smell, half this room does not. And that's what makes odor management so challenging, is that each of us perceives those odors differently. Now, in organics recycling, we have odors created by a mix of several volatile compounds. Volatile meaning that they become gaseous, they are emitted to the atmosphere. These volatile compounds are inherent to the process of decomposition. Whether you're a composter or running an AD plant, you are managing decomposition. And by virtue of that, you are managing how these organic chemical bonds are broken and how they become part of the food chain for microbes. And so managing this process of biochemical decomposition is an important aspect of odor management. Organics recycling odors are transient, they vary in time, they're changeable because they are chemically modified by atmospheric conditions. They are subjectively offensive, just as we pointed out with the blue cheese dressing. Some people like it, some people don't. However, they are all manageable. Odors are a manageable problem. Every facility in the organics recycling industry should have an odor management plan. An odor management plan has three major components. What are your sources of odors and your options for mitigating them? And we've got several great speakers today who are going to talk about mitigation strategies and technologies. How do you monitor for odors? Monitoring is important to understand what's going on in the world around your facility. And then complaint response. We'll spend some time this afternoon talking about how do you structure an effective, workable, meaningful complaint response plan. The key to understanding your sources and your mitigation options is to understand the odor chain. The odor chain consists of the formation of gaseous chemicals that are emitted to the atmosphere at a facility, the transport of those chemicals through the environment by some meteorological event, and then the reception and perception of those chemicals by the receptor, which in this case is the human nose. And Dr. Dalton at her presentation is going to talk a little bit about the human genome and why odors in the nose and our ability to smell is so unique and so very complicated. Now, odors come from all aspects, most of the aspects of organics recycling. In this hypothetical process flow diagram, we have the potential for odors where they come into the facility, where they are prepared and or mixed for further processing. The digestion process itself, because it's in an enclosed reactor, tends to be relatively odor-free for obvious reasons. But whatever you do with the residual from digestion can be an additional source of odors, whether you send it to a composting facility, whether you compost it on site, whether you send it to land application or some other use. Number of sources of odors at a facility, and it's important to really drill down and understand all the different sources in a facility. And they can be as varied as stormwater management ponds. Many of these stormwater management features on a site will have fines that get washed in by the rain. That creates a source of odors. If you're working in bare earth or on an unimproved site, little stormwater puddles will form after a rainfall. They can be sources of odors, as well as any kind of processing facility, a biofilter. Biofilters are remarkably effective at reducing volatile organic compounds, which are the sources of odors. But they're only effective to about 98 to 99%. Well, you think, well, that's pretty good, 98 or 99. That means that 1 or 2% is getting out. And we now live in a society that is increasingly intolerant of inconvenience. And because of that increasing intolerance, people complain about odors very, very frequently, even if they, to the operator or to us as professionals, we don't see them as unpleasant odors. Others do. I had the pleasure of working on a project near Philadelphia last year where they were composting leaves. Now, you think, well, leaves, composting leaves, that's not hard. Many people do it in their backyard. But people objected to that earthy smell of composting leaves. Again, it goes back to the fact that we're all individuals and we all have individual concerns and feelings about odors. The field of odor science is a well-studied field, and there are several different concepts I want to run through just to get everybody on the same page with what are the key terms in the field of odor science. So odors are quantified in different ways. Now, keep in mind, we're talking about a chemical concentration in atmosphere. So 1 unit of measure is the mass of that chemical in a volume of air. These can be expressed as odor concentrations. You might see the term milligrams per cubic meter, milligrams of that chemical, that odorant, in a cubic meter of air. You might see terms called odor intensity, which tends to be a numerical, dimensionless numerical scale of intensity. Persistence is defined by a concept called Stevens' law, which we'll get to in a minute. Odor character, which is sort of a way of describing the nature of an odor. And then hedonic tone, which is a measure of unpleasantness. So various odor concentration terms you might find in the literature are things like the odor detection threshold, which is also called the perception threshold. And that is usually the minimum concentration of an odorant that you can that the human nose can detect. It is often defined as 1 odor unit per cubic meter. Odor unit is a European term, European unit of measurement. But it's normally in this country, we use the concept detection threshold. So that is the minimum concentration at which you can detect something. You don't recognize it, but you detect it. And every single one of us has been in a situation where you've caught a whiff of something and went, what's that? And you don't recognize it, but you can detect it. Above the detection threshold in terms of higher concentration is your recognition threshold, which is the concentration of a chemical in which you can recognize what that chemical is. You walk into the grocery store, you walk past the floral section, you can smell the flowers. Now, part of that is visual because you're looking at the floral section and your nose says, oh, I smell flowers, your eyes are looking at flowers. So, but the recognition threshold is where you can recognize the nature of the chemical that you're smelling. Dilution to threshold, which is abbreviated D/T, is the concept of diluting an odorant with sufficient volumes of fresh air to reduce that odorant's concentration below a certain threshold, which we'll get to. Odor units and odor dilution units are also similar methods of defining concentrations. So the threshold odor concentration, or the detection threshold, as I said, is the minimum concentration at which an odor can be detected as being present in an environment. The recognition threshold, that concentration in which you can recognize what the odor is. The RT is usually somewhere between 2 times and 10 times the detection threshold. The potential for an odor to occur depends on volatility. How easy is it for that chemical to convert from a solid or liquid phase to a gaseous phase, to leave the processing environment as a gas? You know, it's correlated with the odor index to some extent. One definition in the literature for odor index is that the index is 10 times the log 10 of the odor concentration. For example, if an odor is measured at 500 odor units, the odor index is shown in this calculation on the slide, 10 times the log 10 of 500, 10 times 2.7 or 27.0. So here we see some volatility issues. How easy is it for these chemicals to become gases? So we see common odorants that we find in organics processing: ammonia, hydrogen sulfide, methyl mercaptan, which is a sulfur compound, dimethylamine, and that's a nitrogen compound, dimethyl sulfide, methyl ethyl ketone, also known as butanol, and skatol, which is the lovely smell of a skunk. So we see here the molecular weights of these chemicals and their boiling points. So ammonia boils off as a gas at minus 33.4 degrees centigrade. So it's very rare to see ammonia in liquid form. In fact, it's probably impossible to see it in liquid form in an organics processing facility. It's going to be a gas. Some of these other chemicals have higher boiling points, And so they have different detection thresholds. These are parts per million by volume. Let's put that concept of part per million in context. 1 part in a million parts is the same as 1 inch in 15.8 miles. Think about that. 1 part per million is 1 inch in 15.8 miles. It's also essentially the volume of a ping pong ball in an Olympic swimming pool. So here we have detection thresholds for ammonia, 0.037 parts per million. Okay, back to a ppm. 1 ppm equals 1 inch in 15.8 miles. So very low detection threshold for ammonia, H2S even lower, methyl mercaptan, and so forth and so on. Look at skatol. An odor detection threshold of 7.3 times 10 to the minus 9 part per million by volume. Very, very low. And that's an important concept to understand in odor management, is that some of these chemicals become gases very readily. Those gases are easily detectable by the human nose. So here we see some odor indices in a paper published by McGinley from St. Croix Sensory in 2006. Various odor index values based on the log value of the odor units, and different examples of how what those odors are. So rendering plant uncontrolled exhaust, fairly odorous material, obviously. Notice number 2, venting anaerobic digestion gases, which is why we're here. Sludge centrifuge vents, primary clarifiers. Obviously, wastewater treatment and sludge management facilities have a lot of potential odor, and so forth and so on. And then you get down to the bottom of the list, and odor units of 2, ambient odor level, usually considered just noticeable. So that has an odor index of 3, but you can see how these values change with the nature of the source. Dilution to threshold is the concept in which, and we were all taught as young environmental scientists, never say dilution is the solution to pollution. But in terms of odor, it is. Dilution is how you reduce odor concentrations below the detection threshold, or recognition threshold, which is key. So dilution occurs in the atmosphere, and we'll talk a little bit about how that happens. The concept is, how do you dilute an odorant to a threshold concentration where the receptor can no longer recognize the odor? And of course, citizens who live downwind are the receptors. This is measured with what's called an odor panel, and there's an ASTM procedure, E-679, for how an odor panel operates. This is usually 8 or more people who test a sample by smelling it. The test is calibrated with butanone, and each person sniffs the sample at different concentrations, and they report whether or not they can detect it. A dilution to threshold then becomes the number of dilutions of that odorous chemical with odor-free air that dilutes it down to the point where half that panel can no longer detect it. So for example, if you have a cubic foot of odorous air and you need 3 cubic feet of clean air to dilute it below the panel's threshold, then the D/T, or dilution to threshold value, is considered equal to 4. And we'll get into the meaning of that with regard to odor modeling here in a minute. Odor intensity measures the strength of an odor. It's obviously a function of the concentration. It's measured against a reference standard, usually a butanol compound. And Stevens' law, which was an 18th century English physicist who came up with a mathematical relationship to describe the relation between the magnitude of a physical stimulus and the perceived intensity or strength of that stimulus. This is Stevens' law graphed out. Perceived intensity on the ordinate, concentration on the abscissa, where you are plotting the perceived intensity of a butanol scale against the concentration as an odorant. And these plot out based on certain constant values as either pervasive odors or non-pervasive odors. For example, this is the mathematical formula for Stevens' law. I equals a numerical constant called K times the concentration raised to the power of another constant. So the higher the N value, which ranges between 0.2 and 0.8, the higher the N value, the more non-pervasive an odor is. The perceived intensity of that odor dilutes very quickly. For example, car exhaust, solvents, all dilute very quickly, and you lose that perception that that is a pervasive odor. Something with a lower N value is pervasive. Pervasive odors would be things like cigarette smoke, hydrogen sulfide, those kinds of things that you can persist in the environment for a long period of time. So pervasive, an acronym for, or a synonym for pervasive might be persistent. A pervasive odor is a persistent odor, very hard to dilute down to the point where it's no longer detectable. We have odor character as a way of quantifying odors, which is a series of standard descriptors that provide a way of referencing a vocabulary about odors. And so there is what is called the odor flavor wheel. I don't know if you've ever seen one of these. These are interesting. Here we have a wheel. On the inner circle of the wheel, we have descriptions of the odors: grassy, woody, fruity, fragrant, solventy, earthy, etc. We have additional descriptors in the outer wheel that further describe and refine what the inner wheel is characterizing. So for example, if we're talking about a fruity smell, it could be citrusy, it could be a soapy type of fruity smell. And on the outer ring of the odor wheel, we have the chemical that is responsible for that smell. So back to our example, we have a fruity smell that smells kind of citrusy, sort of the smell you get when you cut open a lemon or an orange. Chances are that chemical is called D-limonene. That is the chemical making that smell. And as you look at this wheel, you can find some of them are less favorable descriptions, shall we say. And that you can see on the outer ring what it is that the chemical is that causes those smells. Odor wheels are often useful for helping people to understand what they are smelling. If you get a complaint from a citizen who's, when you get a complaint, they always make it very emotional, very angry, very argumentative, and they always say something extreme like, smells like, a dead body. No, it doesn't. That's a particular smell called cadaverine, which is so unique, you really, once you've smelled it, you never want to smell it again. So one of the values of these odor wheels is to get people to say, well, is it earthy? Does it smell like a sewer? Does it smell rancid? What are the different types of odors? And some of them are unpleasant, and they require the use of unpleasant terms. But that's the nature of the beast. The last method of measuring odor concentration is the concept of hedonic tone, which is a measure of pleasantness or unpleasantness, ranges from 0 to +10 to -10. It's subjective, but again, it's a way of getting people to quantify and not qualify their reaction to an odor. So if you say, Mr. Smith, I'm sorry you smell an odor from what you think is coming from my facility, would you characterize it on a scale of -10 to +10, where -10 is awful, +10 is not bad? Try to get them to quantify and zero in on what are they really smelling instead of just reacting emotionally. And we'll get into this more during communications later today. So the kinds of odors that we find in organics recycling that tend to be persistent and unpleasant are the sulfur compounds. mercaptans, H2S. Of course, H2S is a very dangerous gas from a human health standpoint. Various nitrogen compounds, usually products of decomposition. Amines being the most notable. And then volatile fatty acids. Every digestion facility in the world manages the decomposition of organic material into volatile fatty acids. Fortunately, most of those stay enclosed in the reactor, but volatile fatty acids can create significant odor issues. In sulfur, the sources of sulfur in odors are usually the amino acids in proteins that when they break down aerobically in a composting facility, they form mercaptans. When they break down anaerobically in a digester, they form hydrogen sulfide. And these are the kinds of things that create significant odor issues at both composting and digestion facilities. Hydrogen sulfide is normally in equilibrium. It's parts of it are very water soluble. If the pH drops below 7, H2S becomes, thank you, Terry, becomes a predominant chemical. Total reduced sulfur compounds are H2S, methyl mercaptan, DMS is dimethyl sulfide, DMDS is dimethyl disulfide. Some states regulate, for example, New Jersey regulates TRS. So they look at the total reduced sulfur compounds being emitted by an organics processing facility. Each of these types of sulfur compounds has to be treated a little differently. DMDS is very hard to remove from an aeration gas stream. The biological sources of nitrogen are usually the decay of organic nitrogenous compounds that produces first ammonia, but then you also get into producing amines as well. VOCs, predominant air pollutant in organics recycling. Volatile organic compounds regulated in states like California because they contribute to ozone formation for photochemical fog. Now, the odor load that you have to manage is usually calculated as the concentration in terms of dilutions to threshold times your volumetric flow in cubic feet per hour. This is usually applicable to a point source release where you have a total mass load of chemical that you need to reduce in order to meet some form of boundary emission standards. In this photograph here of the stack of a building, you see in the lower right-hand corner a measuring device. They're taking an air sample. I used to run an engineering firm where we did stack testing, and we'd climb 300-foot tall smokestacks to take an air sample. And you think, okay, it's a concrete column, 300 feet in the air, very stable. No, it's not. It waves back and forth in the wind 2 to 3 feet, and there are a few things more unnerving than hanging onto a ladder while it's moving. Surface odor emissions rates is another method of calculation. You have the concentration and dilution to threshold times your volumetric flow in cubic feet per hour divided by the surface area of sampling. Now, this is more applicable to area sources. So we see a lot of this kind of testing being done in composting, where you take basically this is a odor emissions sampling device. These are somewhat imperfect methods of capturing samples, but it's all we have. They capture the sample for later chemical analysis. So we have different odor types depending on the feedstocks. We see as the byproducts of decomposition, as we've been talking about, carbohydrates break down into alcohols, volatile organic acids, ketones. Our proteins, carbon, nitrogen, sulfur compounds break down into the mercaptans, ammonias, amines, VOAs, and lipids, which are the fats in various organic feedstocks, have somewhere decomposition products. These are the main sources of odors. Some data that's getting a bit old, but it's good data from Van Derm in 1990, looking at the mean concentration in biosolids processing of ammonia, hydrogen sulfide, DMS and DMDS, and the odor concentrations in dilutions to threshold. So for dimethyl sulfide, you need almost 500 volumes of clean air to dilute that volume of odorous air down to the point at which your odor panel will not be able to, 50% of the odor panel will not be able to detect it. That's a very significant dilution to threshold. These are some emissions data published in 1999 from food waste processing, showing the kinds of emissions. These were measured in terms of grams of chemical emitted per ton of material processed. Significant amounts of alcohols from the decomposition of food waste. Not surprising. Source testing data from an anaerobic digestion facility in Italy processing the organic fraction of MSW is shown here, published in 2009. They analyzed the feed, pre-digestion feed, the digested material after an HRT of 40 days, and then post-digestion after an HRT of 50 days. And we see here the investigators measured oxygen demand, milligrams of oxygen demand per gram of total solids. They measured odor units per square meter per hour and volatile organic compounds in parts per billion by volume. Now remember, a part per million is 1 inch in 15.8 miles. 1 part per billion is 1 inch in 15,800 miles. Think about that for a minute. So we see here in the feed significant oxygen demand. Oxygen demand drops off after HRT of 40 days, drops even further another 10 days. But notice the odor units. They actually start, according to in this data set, odor units went back up after digestion in the post-digestion period. Volatile organic compounds also went back up in post-digestion. Also notice significant variation in the data in terms of means and standard deviations. But interesting data, still significant odors in the digested material after a 40-day HRT. So that was odor concentration and some of the odorants that we have to manage in organics recycling. Let's now look at the second part of the chain. We know how these materials are being generated. We know where they're being generated. Question now is, how do they get transported? So odors are air pollutants, and those mechanisms that remove air pollutants from our air work in many cases to reduce odors. So obviously dilution, as we talked earlier, we have dilution to threshold. The more you can dilute an odor, the better. You can also get some reduction of odor by settling of particulates, because in many cases dust particles have odor molecules adsorbed to the surface. And so those particulates can be washed out by rainfall, and that knocks down some of the odor. I mean, everybody here has probably walked outside after a period of rain and noticed an improvement in air quality. The air smells clean. And that is where odorants that have accumulated in the atmosphere are literally scrubbed by the rainfall. Photochemical reactions can reduce odorants, and absorption by plants and soils, which is one of the big reasons why a well-vegetated buffer around any organics processing facility is advantageous to reducing both odors and dust. Now, this concept of atmospheric dilution is called dispersion. How do these odorants disperse in the atmosphere? And it's created by two phenomena. One is simple, surface wind speed. The more the wind blows, the more clean dilution air is diluting that odorant. And the other concept is called vertical movement, which is air movement in the atmosphere caused by solar heating and by temperature differences as elevation increases. So we'll switch gears here. We'll do a little bit of meteorology 101. One thing that's useful to understand about odorants and surface winds is what is the wind pattern at a given site. Now, winds are very variable. They change a lot, but over a period of time, you can plot what's called a wind rose. This is a wind rose, and this is 360 degrees around the facility. This takes 5 years worth of data on wind speed and direction and plots it. So what we see here is the longest bars on this chart are the most frequent direction the wind is blowing towards in this graph. You can also do a direction the wind is blowing from. In this graph, we see the wind is predominantly blowing to the south and to the south-southwest. The different colored bands represent different wind speeds. So in terms of miles per hour, the yellow band is 2.7 to 5 miles per hour. So that in the southerly direction is the predominant wind speed. What this helps you do is understand when you're siting a facility to organize your site in a way that puts those things that are odorous out of the main wind pattern so that odors don't get carried downstream. The other aspect of dispersion has to do with this concept of vertical air movement. That air temperature decreases with elevation. Those of you who are weather geeks like me will be on an airplane trip and will look at that little TV screen in the seat in front of you, and you'll look at the data for this flight. And you're at 36,000 feet, and it's minus 60 degrees Fahrenheit outside. Temperature decreases with elevation. This is called a lapse rate. And there are a couple of meteorological concepts. One is the actual lapse rate. The other is called the adiabatic lapse rate. Adiabatic meaning a theoretical change in temperature, which is driven predominantly by a reduction in atmospheric pressure. As a rule of thumb, adiabatic lapse rate runs about 10 degrees centigrade per kilometer of elevation. Because of this decreasing temperature phenomenon with increasing elevation, you have these different classes of atmospheric stability. You have unstable air, where the actual lapse rate or the actual rate of temperature decline with elevation increase is greater than the pressure driven or the adiabatic lapse rate. So you get an acceleration, a vertical acceleration of air. That creates greater turbulence. Turbulence means more dispersion. So unstable atmosphere is beneficial to odor dispersion because you have vertical transport accelerating. A neutral stability, you have actual equal to adiabatic, so your buoyancy is 0. In a stable atmosphere, you have the opposite, actual being less than adiabatic, and so you have very low turbulence and very limited vertical transport. The extreme of a stable atmosphere is called a temperature inversion, in which temperature actually increases with altitude up to about 250 meters. And that actually traps air at the surface. And when that air gets trapped at the surface, so too do the odors. So it's important to understand what is the frequency of temperature inversions in a particular area. This looks at this somewhat in a graphic form. So we have here an unstable environment. Temperature of air, the temperature decreases as you rise in elevation. And so the air tends to move upward and away. With a stable environment, just the opposite. It tends to want to drift back down to the surface. And with a temperature inversion, you get this boundary layer at about 250 meters, and everything gets trapped below it. So when you see in temperature inversions, you'll see significant air quality issues due to ozone in big cities. Mexico City is well known for inversions causing air quality problems because it sits down in that mountainous bowl. So we use odor dispersion modeling to try to understand what are the potential impacts of odors. These are mathematical simulations of odor dispersion and dilution that we use to evaluate how odors might move around and to determine how what kind of impacts might be on a neighboring area. One of the best models to use is one by EPA called ISCST3, their Industrial Source Complex Short-Term Model 3, which is a Gaussian dispersion emissions transport model It takes into consideration local topography and meteorology, determines the emissions transport based on your source size, location, and strength, and the output plot is odor concentration isopleths, or lines of equal value. So we see here on this plot around this biofilter, we see various lines of equal dilution to threshold. These are called the isopleths of equal dilution to threshold. The red line here is a D/T of 5, which happened to be the regulatory standard at this time when this study was done many years ago in California. So what the regulators are saying is, we will not allow any odorant to be at a greater than 5 dilution to threshold. So what the odor model does is it plots where is that D/T equal 5. And that helps understand, is the facility going to be in compliance at the property line, which is where the standard is applied. So odor modeling results give you some concentrations at which odors can cause a nuisance, depending on the intensity of the odor. Dilution to threshold is fine. A 5 is probably fine for some odorants. It's not going to be enough for other ones based on what the data we looked at earlier regarding detection thresholds. But from a regulatory standard, because regulators like to have an easily measurable standard against which to reference things, and understandably, odors greater than a dilution to threshold of 5 are generally perceived as a nuisance. Our second aspect of how to do an odor monitoring plan, odor management plan, is monitoring. How are you going to know there are problems? So monitoring protocols need to be developed to have a daily routine evaluation. And it's really important that you not use on-site personnel. Those of us who have been in the organics recycling industry for any length of time have less than objective odor nasal detectors in our noses. Quite honestly, you get used to an odor, and it becomes very hard to detect that odor off-site. So consider using people that don't work at the facility every day, maybe somebody from your home office, or somebody who's not involved in the plant every single day. If they do detect odors, there's a need to investigate the source, obviously alert management, try to evaluate the off-site impacts, develop remedies if you can, and document everything. Can't emphasize that enough. You have to document everything, given we live in an increasingly litigious society. I recommend every organics recycling facility install a meteorological station on site. I buy mine from Forestry Supplies. They're usually less than $1,000. They measure wind speed, direction, rainfall, the very basic stuff you need to know about the on-site meteorology at your facility. And they usually tie back into your desktop PC so you can keep track of the data. One downside is they sample about every minute, so you end up with a couple of terabytes of data after about a year. This is the odor monitoring protocol at one of my clients' facilities in Minnesota. This is both a biomass processing plant for a thermal mass burn plant and a composting facility. There are monitoring stations in which a field olfactometer, it's called a nasal ranger. It's a measurement device, and I think we'll have some people talking about that later today. It's a measuring device for measuring dilution to threshold in the field. So every morning at 5:30, an industrial hygienist makes this circuit measuring dilutions to threshold. Why at 5:30? The air is heavy, it's quiet, it's still. That's the best time you'll find odors close to the surface, because the atmosphere has not been heated up by the sun. And some of these monitoring stations are a quarter of a mile away and further. But that is and he does not work at the facility, so he has a clean nose. He can smell smell quite well, and so he runs around this circuit every morning at 5:30, measuring dilutions to threshold. And that concludes our first presentation on odor science. My contact information is here. Let me see how we're doing on time.
Right on the button.
We're a few minutes early. Any questions or comments on that first little bit of technology or technical stuff? Yes, sir.
On the nasal ranger, how long is the training to use it?
I'm sorry?
How long is the training to use the nasal?
Question is, how long is the training to use a nasal ranger? I've not gone through that training myself. I believe it's a couple of days. Anybody familiar with that tool and how to use it?
I'll talk a little bit about
Okay, you'll talk about it in your.
it. A little bit, yeah.
Okay. Stay tuned.
Drawbacks in it too, if you don't mind.
Stay tuned.
So as a follow-up, challenges that we face from our company is very limited, in some instances, pollution to threshold. I've met a lot of odors from hog farms and chicken farms and meat plants, and their velocity of the fans are high, dispersing quickly, and basically the complaints are there. But at a distance, at a great distance, the odor's minimal or less than it was. So the challenge is that for us is to demonstrate to a customer application and evidence. So are you, in your presentation before, did you have any type of validation constructs of, when you say you gotta get it down, and what this is?
Well, it's an interesting point because those of us in the organics recycling industry often say people smell with their eyes. As I said earlier, you walk into the supermarket, you walk past the florals department, you will and your nose detects the odor of flowers. Your eyes have already recorded the fact that you're looking at flowers, so your nose knows what to expect. In organics recycling, if you can see a facility, if you can see a hog house or a chicken house, chances are you are going to think about what's in that building, and the mind is going to say, okay, there's likely to be an odor associated with that building. And so when they will be more attuned to detecting it early if they can see it. Conversely, if you're at a densely vegetated site, you got a lot of vegetated buffer, people may smell an odor and they'll go, what's that? I'm not sure what that odor is, but I smell something. Now, Dr. Dalton is going to talk about that a little bit, and so is Mike when he presents later today. The short answer is, there's no numerical standard to get below that you're absolutely going to be safe unless you get down to below, an odor units of like 2, which, as I showed in the one slide, is the level of which most people think is a clean air. Now, getting down to that level could be technically impossible. Sir, you had a question?
Yeah, actually 2 questions. So those who focus on sulfide, have you had any experience with volatile fatty acid odors and specific strategies for removing those?
My experience with them is primarily from a composting standpoint, and the key there is basically lots of air. Try to degrade those volatile fatty acids down to their components as quickly and as you can.
We're actually in a fortunate situation where our process is anaerobic. So we have an anaerobic situation where we have VFA formation, but it's also not for methane generation. It's not an anaerobic digester. So it's just those first acetogenic phases.
The only answer I've got for that would be to try to get it as aerobic as you can, as fast as you can. There really are no good control methods that I'm aware of, but I'll defer to the others in here who are going to talk about control technologies for VFAs.
One of my slides will have VFAs, enlightening that.
Yeah, this is one of our technology providers who'll be speaking at lunch. Any other questions before we move on? Tibor?
On the last, the nasal ranger measurement.
Mm-hmm.
Can you tell a little bit about their action plan? So if he detects something, what do they do, if any? Like what? I know there are many examples. How this one specifically worked out?
Well, the reason they do this is because the citizens who have complained about odors arising from this facility don't call the facility, they call the Minnesota Pollution Control Agency. Well, MPCA's offices are a good 45 minutes away from this facility. So they will send an inspector out. And of course, by the time the inspector gets on site, the odor's long gone. You know, so what the industrial hygienist does is he does that perimeter walk every morning and records the data. Along with the site has their own meteorological station. So there's a database. And so when the aggravated citizen calls MPCA, MPCA calls the facility, they say, well, here's this morning's readings with the nasal ranger. Here's today's weather. You know, the wind was not blowing in that direction. I don't know what Mrs. Smith smelled, but it wasn't in the facility. So that's really why they do it, is to create a defensive database, really, is what it is.
And who pays for the person?
They do. Yeah, it's an internal cost. Now, that's a Native American, keep in mind, that's a Native American processing facility on tribal land.
Oh,
And there's a certain amount of societal bias going on there that may not affect other kinds of facilities.
but from the regulatory perspective, it becomes even more difficult, correct? Because they don't have any federal power over them.
No,
Even
not
if they-
officially.
Yeah, even if they detect anything, there's no.
Yeah, I mean, yeah, exactly. That's one problem with Native American facilities, but they're very proactive and they accept the fact that while Minnesota PCA does not have legal jurisdiction over the tribe, they are willing to conform to their rules because they want to be good neighbors. Okay, that concludes our first presentation. We'll move on to Pam Dalton, talk about her views. Her biography is in your handout, and I'll just defer to her.
Thank you, Craig.